Section 8.5, partial fractions. Sometimes when we have a rational function integrand, it does not fit into any of the patterns for integration that we have learned. We have to reverse the addition to get back to simpler fractions, fractions that we can integrate with techniques we already know. This technique is the method of partial fractions, and it applies to proper rational functions. In other words, the degree in the denominator is higher than in the numerator. So we're going to do a little algebra review. In algebra, you learned how to combine two or more fractions by finding a common denominator. So here's two fractions, nothing common to both, so we multiplied this by x plus 1 over x plus 1. We multiplied this one by x minus 4 over x minus 4, did the algebra, and we got this fraction. This is the fraction we're going to be starting out with in partial fractions, and we're going to have to get it back to that so we can integrate. By the way, just a quick trick, if you have fractions that do not have common denominators, a quick way to combine them is this product plus this product over this product, if this is a plus between, and if it's a minus, you have a minus. Nice little quick way to do it. So this illustrates a theorem from advanced algebra that says that every rational function, no matter how complicated, comes from adding similar fractions. So for integration purposes, we prefer the two fractions instead of the single one. So we now know from going from here to here, we know that this came from these two fractions being added together, and we can anti-differentiate each of these. Each of these is a u prime over u type form. So this will be 2 times natural log of absolute x minus 4 plus 3 times natural log of x plus 1 plus my constant c. So the focus of this lesson is to learn the algebraic techniques for determining the constants in the numerators of a partial fraction. This is called the decomposition of the partial fraction. Now, in this video, I am only going to address linear factors. There are other factors, and in class, with the rest of the notes you will see, we will discuss those in class. I don't want the video to be that long. So first of all, here's our first example. We know that this factors, my divisors, are linear. So what we do is we know that this came from these two denominators, and so we're going to split this fraction and call it a over x minus 1 plus b over x plus 2. And it really doesn't matter which one you call the a or the b. That doesn't matter. The number you get on top for a should be the same whether you call this an a or a b. And the number you get on top of x plus 2, which I called b, should be the same if you call it a. So what I like to do with this equation, I have stated that this is equal to this, is I like to now write this like a over x minus 1 plus b over x minus 2, and we are going to get common denominator for both of these fractions. So what we are missing is the x plus 2 factor for this one and the x minus 1 factor for this one. Now what you are looking at is this equation, that 1 over x minus 1 times x plus 2 is a times x plus 2 over x minus 1 times x plus 2 plus b times x minus 1 over x minus 1 times x plus 2. Now, the reason I actually like to do it like this is because in this equation, if the denominators are equal, then the numerators are equal. Okay, so I don't like these instructions that I wrote a long time ago. I like to actually get my denominators to be the same so that I can focus on the numerators. Now, this is an equation with several variables, but here's something that we know. If x is 1, this term is going to drop out, and I can substitute 1 for x, and I can solve this equation for a. If x is negative 2, this term is going to drop out, and I can substitute negative 2 here and solve for b. And that is exactly what I'm going to do. So letting x equal 1 makes this 0, which lets me find that a is 1/3. Using the same procedure, letting x equal negative 2 will make this factor 0 and this term 0, and b is negative 1/3. So the constant that goes with the denominator of x minus 1 is 1/3. The constant that goes with the denominator of x plus 2 is negative 1/3. And that's what I meant why it didn't matter which you called A and which you called B, because whatever you do, you should get the same constant on top as me. And now we don't write it like that, so we would write it like this. Now I have two fractions and I can anti-differentiate each of them using techniques we know. If I bring this 1/3 out in front, we have u prime over u. If I bring this 1/3 out in front of the integral, I have u prime over u. So we get this becomes this. They both have the coefficient of 1/3, which is convenient, which means I could factor 1/3 out like this. And I have technically ln A minus ln B, which is ln of A over B. And there you go. When the divisor has a repeated factor, it is not possible to find all of the constants in that way that we just did. There is a special procedure which must occur when writing the fraction in decomposed form. So find as many constants as possible by substitution and then find the rest by equating coefficients. When we factor the denominator, we have a repeated linear factor. So my setup becomes slightly different. I have a over x plus b over x squared plus c over x minus 2. So what you're setting up is the possibility that, for instance, one fraction has a 2 in the denominator, and maybe this one has a 4 in the denominator. Okay, so let's look at just something you would have learned how to do back in elementary school or middle school. Notice that I have these three fractions. Well, what do I need to do? Notice this is 2 to the first power and 2 to the second power. Well, I can get common denominator and add those two together. That gives me 3/4 plus a third. And now I can get my common denominator, multiply this by 3 over 3 and this by 4 over 4, or use my nifty little SAT trick. And here is my sum. So what we are doing is going from this back. Notice that this fraction right here could have come from simply 3/4 plus 1/3, but it also could have come from 1/4 plus 1/2 plus 1/3, and that is the situation we have to set up. It's not good enough to stop here. This could have come, this sum, from here. So this is why when we have a repeated linear factor, we have to account for that factor to the first power or to the second, or if it's got a higher degree than that, continuing on. And now we're going to do the same thing we did before, which is get common denominators and equate the numerators. Right? So my common denominators would be, I need x squared, so this fraction is missing the x times the x minus 2. This has the x squared, but it's missing the x minus 2, and this is missing the x squared. And so now I can just look at my numerators. 2x plus 4 equals these. Now, it says up here in the instructions, do as much as possible by substitution. Well, if I let x equals 0, that term will drop out, and that term will drop out, and we can solve for b. If I let x equal 2, this term will drop out, and this term will drop out. I can solve for c, but that still doesn't give me a way to solve for a. So going to the bottom of that page, let's let x equal 0, which, as I said, this term will drop out and that term will drop out, and it leaves me, when x is 0, it leaves me solving this equation when x is 0, b is -2. So we have the b. Now let's let x equal 2, substitute 2 everywhere you have an x. We know we're going to get 0 here and here, and I get c to be 2. What I don't have is a. Well, I'm going to show you another method for finding a, but here is the absolute easiest thing. Why don't you pick any other number for x? We've already picked 0 and 2, so let's pick another one. What about x equals 1? When I substitute 1 into this equation and my value for b and c, then I'm left with a, and I can solve for a. Now that is actually the easiest way to do it. This is called the Heaviside method. It's very elegant. Now let's go back up to the middle of the page and look at another method. And when you're actually having to work partial fractions with higher degrees, you have to use this method. So from this step, I like to call it collecting coefficients. What that means is distribute your AX across this, your B across this, and your C. And let's look, when I distribute, I get, here's my quadratic terms. I do not have a quadratic term over here. So my quadratic term coefficient is going to be 0 because there's not one over here. Here's my linear terms, and my linear term coefficient is going to need to equal 2. And here's my constant, no x, and my constant is going to need to equal 4. Writing this out with my quadratic term that's not really there, we can equate the coefficients. I know that a plus c, the coefficient of my quadratic term, has to be 0. I know that negative 2a plus b has to be 2. And way down here, negative 2b has to equal 4. From here, I can find b. Now that I have b, I can go to this one and find a. And now that I have a, I can go to this one and find c. It's very nice. It's not very hard. And now you have your a, b, and c, so we can do what we could have done after the bottom of the page. Our a, b, and c were written like that, and here it is. We still haven't done the problem, which is to anti-differentiate that. So the integral of this fraction becomes the integral of these 3 fractions. And we can treat each one of them independently and anti-differentiate using the methods we know. We know that negative 2, I could keep it as a coefficient of 2 and deal with that negative sign and make that negative sign on the x, which gives me 1 over x. This one integrates to this, and this one integrates to this. I can put together my 2 natural log ones, and now that I don't have that negative sign anymore, I have 2 times multiply this times this gives me that, plus 2 over x plus c. Example 3, here's what we want to integrate. We're going to factor the denominator. You can see I have all linear factors. So I'm going to write my fraction like this, in decomposition form, get all of the denominators to be the same so that we can notice only the numerators. So this equals these. And again, we're going to go through our process of eliminating. Let's let x equals 0. We'll drop these 2 terms out. Let x equals negative 2 drops these 2 terms out. And let x equal 1/2 drops these 2 terms out. And you'll be able to solve for everything. So when x is 0, substituting 0 everywhere you have an x, lets us find a to be 1/2. When x equals negative 2, these 2 terms are going to drop out. And we can find c to be negative 1/10. And when x is 1/2, these 2 terms will drop out. And we find b to be 1/5. Now we're going to rewrite all the fractions. Notice that what I have done is I have thought about this as 1/2 times 1 over x, and 1/5 times 1 over 2x minus 1, and minus 1/10 times 1 over x plus 2. That's because it makes it so much easier in setting the integral up. And now that I have that set up, I can anti-differentiate each of them. And these have the same coefficient, so I can think about this as 1/10 times natural log of absolute 2x minus 1 minus natural log of x plus 2, which is going to be this over that in these same absolute value bars. And we have that. And you can leave it like this. That's good enough. And we will stop with these examples because you will only be doing linear and repeated linear for homework. Your TPs are 5, 7, 11, and 13. See you next time.